talk a little bit about chapter 13. Chapter 13, I've already said, is my favorite chapter of all of them that we get to do. Unfortunately, I think your book spends a lot of time on a lot of good topics, but it completely just breezes past Kepler. I think Kepler, the Kepler's law stuff, is one of the most important things in chapter 13. And I want to make sure you guys really understand how to do it, how to use it, what it all means. And you will have a problem on the final with Kepler's laws. It might have some of this other gravity stuff in it, but it's going to be a Kepler law problem. And we'll have a short quiz on Kepler's law on Tuesday. So Kepler's laws are easy. I think this chapter mathematically is, the Kepler stuff is easy. It's plug and chug. Some of the gravity stuff is a little hard. So basically we formulated gravity as if the acceleration of gravity was g, and it's always 9.8 meters per second squared, or 9.81. But it turns out that's not the correct way to calculate gravity, that you actually have to calculate it. It's not constant. It depends on how far away you are. And we'll talk about that when we get there. But today, or if you're watching this video, please, the first thing we're going to do is go through Kepler's laws, which is one section of the book. But you got to really make sure you understand it. And to understand it, you have to understand how an ellipse works and what the different variables are in an ellipse. And we'll talk about that, but and we'll even do a problem on that. And then after this, I'll go through the homework 13 briefly and just talk about each of the problems and kind of how to solve them. But I think you'll find this homework significantly easier than a lot of the other homework so far. I actually think that gravity, for the most part, is pretty easy once you know what equations, what the equations do. So as far as studying this part of the book, what I would do is keep maybe a piece of paper with you and write the equations for Kepler's laws and the equations for gravity, and then just keep that somewhere. It's actually somewhat simple because we only have a few equations, and using them is pretty simple. Like I said, this is a lot of plug and chug stuff, but it's also really interesting stuff that you may have never known about how planets rotate and how gravity that keeps you on the surface of the Earth, it's the same gravity as what keeps the Earth going around the sun. Further, we're going to talk about going from Kepler to Newton to Einstein and how things changed. So remember that this class is all about motion. And this chapter should really be the big wrap up of everything. We still have 14 to do, which is all about fluids. And we have 15 to do, which is oscillations and pendulums. But this is really the wrap up of everything I've tried to teach you this semester, is kind of encased in this chapter. And we're going to start by talking about a little bit of history. Hopefully it's interesting to you. I find it interesting. So now, back in mid 1500s, there was a man named Tycho Brahe. He was an astronomer. He specifically used what's called a sextant, which is a lot like a protractor, that you can measure angles between things. And what he did was he measured where every star he could see was in the night sky, every night. And he measured how far away they were. Conveniently, almost every star doesn't move from Earth. They appear to be fixed, except for the planets. And you guys probably know this from the Greeks. The Greeks looked up and they could see Venus and Mars, maybe, or in Saturn and Jupiter, maybe Mercury if they were really good. But they would see that some of the stars actually moved. Well, by the time Brahe was alive, people were really interested in comets. This is kind of that alchemy thing where they felt that comets were omens of disaster, and essentially you could get a lot of credit or a lot of standing if you could predict when comets showed up. So Brahe was super interested in comets. He was looking for comets. He knew what the planets were, but he was looking for comets. But what he ends up having is so much data. He basically has data for years on how the planets move, where they are in the sky. He hires a young man named Kepler. And this is where the story gets interesting. Kepler is a mathematician. He understands math, 15th century math, pre-calculus. He knows math, he knows geometry. And he's going through the data helping Brahe. And Brahe dies. Now, Brahe had a meal, and one story goes he was eating with the Duke or somebody, and he didn't want to get up to use the restroom because that would be disrespectful. So he died. His liver burst and he died. But it's always been rumored that Kepler murdered Brahe. Brahe was kind of a jerk, to put it nicely. So it's possible that Kepler murdered Brahe. A lot of people thought maybe he murdered Brahe for the data because Brahe wouldn't give him the data. But regardless, they exhumed his body and found a lot of mercury in his body, which isn't uncommon for the time. So it's hard to say if Kepler murdered him with mercury, but he may have. I like to believe that he did. It makes an interesting story other than just dying of liver failure. But the true part is Kepler took all of Brahe's data, and Brahe's widow was really upset about that. But he did. He stole the data, and that makes Kepler kind of a bad guy. But what did he do with this data? And this is where things get really, really philosophically interesting. So, and I don't mean to get on anyone's religion, but I want to talk about that for a second. Kepler was deeply religious, and he thought that the planets would orbit in perfect circles because he believed that's how God made the universe. God made the universe perfect, and therefore everything should be perfect. And when he was looking at the data on the planets, basically all he did was he made a graph. He plotted the point each night for the planets and looked at how they rotated around the sun. It's fairly complicated because if you're on Earth trying to put that together, it's not easy, but he was able to. And when he did it, he kept getting ellipses. What an ellipse is it's kind of a squashed circle. So a circle is perfect, an ellipse is something that kind of squashed. And he looked at that and he went, man, Brahe must have messed up. The data must be messed up because the planets obviously rotate in circles. They orbit around the sun in a circle, not an ellipse. And so as they went on and on and on through this, right, he eventually realized that it would all make sense if they were ellipses, if he completely abandoned. This was years of research, and he said, well, what if I completely just abandon the idea that they have to be circles and assume they're ellipses, and everything fit? He put together his laws. Now, for us, this is important because all he did was he had the data of Earth was here one day, and then the next day it was here, and then the next day, and he built up these circles around the sun just from data. He wasn't a researcher. He was a mathematician who just looked at the data and figured out what the data said. And he came up with what we call the 3 laws of Kepler. Kepler's 3 laws for planetary orbits. What we're going to talk about them, and then we're going to talk about how Newton actually proved something totally different from Kepler's laws, which is really important. But if you want to look up the story in the PowerPoint, there's a link to Harvard's version of the story of Brahe and Kepler. It's interesting. It's worth a read. For those of you that just joined recently, hang on. Yeah, it's a cool story. I think they made a movie about it too. A lot of people don't believe Kepler actually murdered Brahe. I do, only because I think it's a more interesting story. So we're going to talk about Kepler's laws, but before we do, this is the most important thing from the chapter if you don't know ellipses. So what an ellipse is it's a squashed circle. So just draw across X and Y, okay? Put a point somewhere to the right and somewhere to the left of the y-axis. This is called foci 1, this is called foci 2. And the idea is if you had two pins and you put a rubber band around them and pulled them and swept it around in a circle, you will get this nice squashed circle. So we know a circle has R is the same, but in ellipse, R changes. And a circle is really just an ellipse where both foci are at the center so that R is the same. Here, it's not the same. So let's talk about the different parts of this and what they are. So for an ellipse, you define a couple things. You have to define the foci and call this foci 1 and call this foci 2, like focus, like a camera. So this distance from the center of the ellipse out, okay, is called the I'm going to call this A. A is called the semi-major axis. And you go out to B, and B is the semi-minor. And if you're wondering, the area of the whole circle would be, instead of pi r squared for a circle, it's pi AB. But we almost never use that. So you have those two distances. So essentially, this thing's 2A wide and 2B lengthwise. But we need to do something totally different now. We need to go to a new slide. What if we only had one foci? And this is important. So if we only have one foci instead of two, what we can do is we still have our semi-major axis, but we can choose a point, and I'm going to do this in yellow, point here and a point here. Now, this point that's close by is called perihelion, and we're going to denote that RP. This point here, we're going to denote RA. That's aphelion. So perihelion, which means close to the sun, and aphelion, or aphelion, which means far. When it's at perihelion, it's close to focus 1. When it's at aphelion, it's the furthest away. So this is the closest it can get, the furthest it can get. And so we can denote, and I'm going to draw this a little bit better, center of the ellipse out to here, and this whole thing. So this whole thing is A. This little thing we're going to call RP, right? And we can see the distance from the center out is A, semi-major axis. But this distance from this point to the foci is called the perihelion distance. So what is this distance? Well, it turns out we call this distance E times A. E is known as the eccentricity of the ellipse. It's a measure of how squashed it is. For a circle, okay, E is equal to 0. For E equal to 0 up to 1, right, but not including 1. So this doesn't include 0 or 1. This is an ellipse. Once you get bigger than that, when E is exactly 1, what you get is a parabola. So that means that you get something that looks like this. And if E is greater than 1, greater than 1, you get what's called a hyperbola. And parabolas and hyperbolas look a lot alike. Hyperbolas are really, really angled parabolas. But the idea for us here is that a parabola, you would come by close and leave. If it's in a closed orbit, the eccentricity has to be between 0 and 1, not including 1. So our eccentricity is basically some number up to 1 times A. If the foci was at the edge here at the perihelion, then E would be 1. If the foci was at the center, E would be 0. And we said that when both foci are at the center, we get a circle. Okay, so E is some measure of how far the foci is from the center. Now, for the other side though, let's look at the other side out to RA. We know this is A, but we want how far is it from the foci. So this distance, which we call RA, is A plus EA. This distance, RP, is A minus EA. And I hope that makes sense to you. So what we have is we have these equations. We have RP is equal to A minus EA, and we have RA, which is equal to A plus EA. And so this is peri, which is close. This is ap, which is far. Okay, so we have those two. And then what is the other one we have that I'm totally forgetting off the top of my head? Why am I forgetting this? Hang on 1 second. I feel like I'm losing something. Sorry, guys. My brain totally just decided it didn't want to work anymore. I'll probably figure it out. Anyway, there's a relationship between, oh, I know what it is. I'm stupid. Sorry, guys. Brain pain. If we have RP plus RA, we get 2A, right? So this little distance plus this whole distance is double A. Now A here, and everyone always gets a little weird on this. A is just the semi-major axis. Astronomy calls it A because that's what astronomers do. But it's the distance to the perihelion or to the aphelion point from the center. So we have these two things. You can interchange all this stuff, and usually what happens is you're given two things. You might be given A and RP, or RA and RP, you know, or A and E, and you need to find all four. So you have RA, RP, E, and A that you need to find from these things. So in this first case, if I knew A and RP, I could get EA from this equation, and then put that in here to get RA. If I knew these two, I could get A, and then I could use either one of these to find E, and on and on and on. We'll do that later. But these are your first three equations, and they are simply based off of the math of an ellipse, okay? So Kepler's first law is that the planets orbit in ellipses, and the sun is at one foci, and nothing is at the other. Now, you might be thinking, wow, that must mean that the Earth is really close to the sun and really far away, right? That the Earth at perihelion and the Earth at aphelion is really far away. Well, the Earth is almost a circle. We're going to find that most of the planets, E is going to be less than 0.2. In fact, some of them are even, I want to say Venus is like 0.07. It's almost a perfect circle. most of the planets are almost perfect circles. And we'll talk about why in a little bit. But um, the other idea, and this is a side note, is the Earth is tilted at 23 degrees. I don't know if you guys know that, but it is. And that means when it's on one side of the sun, the northern hemisphere, right here, the southern hemisphere gets all the light. Here, the northern hemisphere gets all the light. Summer and winter for us here in California is when we're on the side that the northern hemisphere is mostly facing the sun, so we have longer days. It has nothing to do with whether it's at ephelion or perihelion or aphelion. In fact, during summer, we're at perihelion. The Earth is at perihelion when we have summer. Meaning, I'm sorry, the Earth is at aphelion when we have summer. So we're further from the sun when it's hotter here, which is kind of weird, but it's because the Earth is actually tilted, and we'll talk about that stuff in a little bit. So equations of the ellipse with one foci are RA plus RP is equal to 2A, where RA is 2A plus EA. RA is the bigger one. Perihelion is always, or I mean, aphelion is always the bigger one. And that's not a 2. A plus EA. And A minus EA. And don't bother with signs. Just take them to be magnitudes. And as I said, just to reiterate this one more time, if this is the foci, this whole distance is A, this is perihelion, this is aphelion, this is the foci. This distance is EA, this distance is RP, and this whole distance is RA. I guess I should draw it out that way. So this is EA plus A. And this is A minus EA gives you RP. It's important to know, and these actually are useful for the Earth. The Earth has a semi-major axis of something called 1 AU. Now, 1 AU is an astronomy term. It's the exact distance from the sun to the Earth. Astronomers like to make big numbers into little tiny numbers. So an AU, if you, and I should probably look it up because I always end up getting it slightly wrong. So it's actually one AU is 1.496 times 10 to the 5th, no, 10 to the 11th. Meters if you need it, but just round it. 1 AU is approximately 1.5 times 10 to the 11th meters. However, a lot of times we're just going to leave everything in AUs. Why AUs? Well, not only is it simpler, but it tells you a reference point. So Mars is not quite 2 AU away from the sun. It's almost double the distance from Earth, from the sun. Jupiter is almost 4 times, so it's almost at 4 AU. Saturn's something like 7. Venus is like 0.7 and Mercury is like 0.3. So they just let you understand. A is from the center to the perihelion, and EA is from the center to the foci Shota. So if we go back to here, this, well, I'll just draw it again. If you wanted to know, having a foci here, and here is what we call the perihelion, and here is what we call aphelion. Here's the center of the ellipse. So this out to perihelion is A, this out to A is also A. This distance from the foci to the perihelion is RP, from the foci to the aphelion is RA, and this little distance here from the center to the foci is EA. And that gives you these 3 equations. just looking at those. Okay, so you also have to know about AUs, but AUs are useful, and it'll come up when we do Kepler's third law, something that makes them super useful that you'll be thankful for. As we said, if EA were equal to 0, then the distance out to RA and the distance out to RP would be the same, because RA is A minus EA. I'm sorry, RP is A minus EA, A plus EA. And if these were 0, then these would both be A and you'd have a perfect circle. If EA is less than 1, you have this squashed ellipse. If E is exactly 1, and a lot of comets are almost parabolic, they come in, circle the sun, and leave, but they actually are really, really high ellipses. And a hyperbola is something that just glancingly shoots by. Now, if E were, say, 0.8, you would have kind of a cigar-shaped orbit. Now, here's the thing that I've already said, and this is interesting. All of the planets, all of them, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus, they all have ellipses that have an eccentricity of about 0.2 or less. Pluto, which a few years ago got demoted, has a really high, it's like 0.4. So what you have is the sun's here and everything's basically rotating in a circle further and further out. And then you have Pluto, which is coming in on this weird high banked long ellipse. That should tell you right away, Pluto is definitely not a planet. It wasn't formed when the planets formed, and it's orbiting some plane that's completely different from the plane of the planets. That's part of the reason that they demoted Pluto and said Pluto wasn't actually a planet. The other reason is Pluto's almost out in the Kuiper Belt, which is really far out on our solar system. There's a bunch of rocks. There's a bunch of rocks out there that may be bigger than Pluto. There's a few of them that are bigger than Pluto. And so Pluto isn't really a planet, or there's maybe a whole bunch of other planets out there. If you want Pluto to be a planet, then everyone gets to be a planet almost. So what they said is, no Pluto. We're just going to say the ones that are in a nearly circular elliptical orbit around the sun and the plane are planets. So we'll talk about that. So if one of the questions I love to ask is, I'll give you the orbit of a planet and ask you to find the eccentricity. And if you find the eccentricity is greater than about 0.2, then you know that it couldn't have formed in our solar system, because anything that formed around our sun is going to have an eccentricity that's very low. That comes from the solar system, they think, formed from a cloud of gases that gravity caused to fall in, and everything starts spinning. So the planets that are part of the solar system would be in the plane and would be spinning in nearly circular orbits, which is interesting. So Kepler's first law is really easy. It's that orbits are ellipses, and the sun is at one foci and nothing is at the other. I don't know why my internet connection is saying it's unstable. So if I lose you guys, I'll pop back in. So that's it. What you really need to know of Kepler's first law is this stuff, these three equations. And like I said, you're usually given two of them. And if you have two of them, you can find the other two. Not too bad. So what is Kepler's second law? Kepler's second law is something called equal area, equal time. And what that means is, imagine the planet Earth going around the sun, and for the sake of the picture, I'm going to make the foci really close here. So let's rethink about this as around the foci if the foci is off at one point, as the Earth goes around, it has some velocity at these different points, okay? Now, if I were to draw out here, let's say I draw two different velocities, velocity 1 and velocity 2, and I make a triangle. If I did this in a straight line, right? So I did this, and I said this is V1 and this is V2, right? So I just drew between the two. There would be some angle between that, and this would be some R, and this would be some other R. If I drew them close enough that essentially this would just be some dB, some small change, and this would be some small angle change, and these two R's would basically be the same, what I would get is that my area of this triangle would be 1/2 height times base, dB times R, okay? And so in order to have equal area, equal time, you could actually do that anywhere. And what you would find if you did this correctly, so say you did it here, and then you did it here, what you would find is that this time, the time it would take, well, let me draw this on its own. I want to actually really show you this. So I'm going to draw this big enough that you can see it. Foci is here. Let's say we want to go from here to here. And let's say in the same amount of time, we then want to go here. For these to be equal areas, so imagine this area and this shaded area are equal. You can see that it's going to go through a larger area, right? That this has to be a larger part of the circumference, right? So this arc length S1 and this arc length S2, S1 is going to be definitely greater than S2. And the velocity is really the arc length over time. Now, for V1 over here and V2, right, if time is the same and S1 and S2, if the time's the same, but S2 is smaller than S1, right, then you can see that in order for, let's rearrange this, time is S over V, so we would have T is S1 over V1 is equal to S2 over V2. In order for them to be constant, if S1 is bigger than S2, right, then that means V1 has to be bigger than V2. They have to be the same. So let's put in numbers. Say S1 is, I don't know, 10 meters, and V1 is 1 times 10 to the 6 meters per second. Then from this, you know that S2 over V2 has to equal S1 over V1, which is 10 over 1 times 10 to the 6th, which is 1 times 10 to the 5th. Now, seconds, I should say. What I'm trying to show you, though, is that V1 is going to be greater than V2, okay? If equal areas and equal time are true, that means that as an object goes around an ellipse, it goes fast, slows. At aphelion, it reaches its slowest velocity, and then it speeds up, and as it passes the sun at perihelion, it's at the fastest point. That is a consequence of equal areas and equal time. That just means that this has to be the same and this has to be the same. And that area is actually this R2 times S2, and this is R1 times S1. In order for that to be true, if R1 S1 is equal to R2 S2, and R2 is bigger, R1 and S1, R1 and let's say R1 is 5 and R2 is 10, right? You can see that R1 over R2 is equal to S2 over S1. S2 over S1, this would be 5 over 10 is a half. So S2 would equal S1 to the half, right? So it would be going half as slow. We're going to actually put that in. I'm trying not to get too technical here because this is what Kepler noticed. Kepler found their velocities were increasing as they headed towards perihelion. And he came up with his law that just says equal area, equal time. That if you do this, you get the exact same thing, okay? So if you take the exact delta t, right? And this is R1 and this is R1 and this is some change of velocity. And you take some R2 and this is also delta t, and so delta V2, delta V1. You find that equal area, equal time. Those two triangles will have the same area, is all he said. Now, Newton, however, realized something much, much easier for us to understand. Hopefully I'm not breaking up. My stupid internet says it's unstable. Now, do you remember, and I hope you do, that for a point particle, the angular momentum is I omega. And for a point particle, I is mr squared, and omega is v over r. So let's turn this into a point particle times v over r, and what we got was mbr, okay? Newton said that in the absence of a torque, the angular momentum is the same, that L is actually the change of the torque with time. So how the torque is changing with time. If there's no torque, then that means that L1 is equal to L2, or M1, I'm sorry, I don't want to put M1, V1 R1 is equal to M V2 R2. And that's really easy to understand. Kepler's second law is easier to understand as angular momentum. If we go out and this is R1 and this is V1, right, at perihelion, and let's say we go out to aphelion, and this is R2 and this is V2, well, let's rewrite these as RP and BP and RA and BA. And what we get here, canceling the M's, is VP, RP is equal to VARA. That right there is super important. If you know the velocity and at any one time, and you know the radius to whatever it's orbiting, in our case, the sun, and you know the radius at any other time, you can find the velocity. The velocities are, well, BR is a constant because angular momentum is a constant because there are no external torques due to the sun. There are no external torques acting on the Earth except the sun, and therefore the Earth's angular momentum is completely conserved. That is actually Kepler's second law. Everyone knows it as equal area, equal time. Newton said, no, it's conservation of something called angular momentum, which is kind of amazing. That you can treat the Earth as a point particle, and using conservation of momentum, you can find the speed of the Earth around the sun, not its rotation around itself, but the speed of the Earth around its sun almost perfectly. It's pretty accurate. This is the only thing you need to know from Kepler's second law. So we have the three ellipse equations, and now we have VARA is VP RP. But in fact, it's really V1 R1 is V2 R2. That's pretty cool. And Newton's way of putting it is so much simpler than this whole area versus time. You can find some nice mathematical derivations of equal area, equal time law, but I prefer just using conservation of angular momentum. It's really nice and simple, and if you understand angular momentum, it's easy. So Kepler's third law is a little weird. He proved it with math. He just put numbers in and rawly converted it. But what he found is something that I'm going to derive. We're getting a little bit ahead of ourselves, but the force on the Earth as it's rotating around the sun is this ma rad, right? Think uniform circular motion. The Earth is rotating with some a rad, and the only force on the Earth is ma rad. Okay. Now, ma rad, a rad, it turns out this force is actually the force of gravity. Newton's force of gravity is formulated differently, and we'll talk about it in a little while. But this is the mass of the sun, the mass of the Earth, and the distance between them. Okay, so this force, that force is equal to ma rad, this right here. Okay, and remember that a rad is not the a that we used in the ellipses. You can cancel the little m's, and you can put a rad is v squared over r, if you remember that. That was where v is the tangential velocity here. So if we put that in for a rad and we put in g, mass of the sun, g is just a constant, r squared, then we get this nice equation that says v squared r is equal to g, mass of the sun. Now, you need to remember that the period to go around was 2 pi r over v. Therefore, v is equal to 2 pi r over t. If I square this, I get v squared is 4 pi squared r squared over t squared. So let's put that in. And actually, I want to go back to leaving this as r over r squared. So when I put that definition of v in, so what I have so far is I have a rad is equal to g m sun over r squared. But a rad is v squared over r, g m sun over r squared. Putting in for v squared, 4 pi squared r squared over t squared over r is equal to gm sun over r squared. And I did change to big R's. So now let's move. No, you don't need to write this down, Sammy. We're going to get somewhere with this though. Let's move the t up. And so we have t squared g times mass of the sun over r. I'm going to multiply by t squared. I'm going to divide by r squared. So t squared over r squared. R to the fourth is equal to, and that got rid of this and got rid of this, 4 pi squared over r. Now I'm going to move all this over. So I get t squared is equal to 4 pi squared g mass of the sun. Remember this term. The r to the fourth over r, I'm just going to turn into r to the third. This right here is one way to derive Kepler's third law. What it says is, assuming all of these are constants, g is a constant, the mass of the sun is a constant, 4 pi squared is a constant, you get the period squared. So the period for the Earth is 1 Earth year squared is equal to 4 pi squared gm of the sun times what in astronomy we call the semi-major axis. So r here is actually the semi-major axis. And I want to talk about this a couple ways, okay? A couple things about this that are very important. Kepler's third law, t squared is gm sun over, did I write that backwards? I totally wrote that backwards. That's unforgivable for an astrophysicist. A cubed. Now, t is in seconds squared. All this stuff ends up being in seconds squared over meters cubed, and this is meters cubed. You can see that this is a huge pain, right? This hurts. G is a big old number. M is a big old number. So you end up doing this big old thing. A is in meters and T is in seconds. Again, I want to say this, 1 Earth year, if you don't know, you could convert this. So you could go 1 year, there are 365 days in 1 year, 24 hours in 1 day, 60 minutes in 1 hour, 60 seconds in 1 minute, blah, 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 blah. Or you can remember pi times 10 to the 7 seconds in 1 year. It ends up being pretty close to 3.14 times 10 to the 7th if you do it. Seconds, it's close enough for us. If you ever need to convert Earth years into seconds, cool. However, one really nice thing about Kepler figuring this out that's weird is Kepler figured out that if T is in Earth years and A is in AU, and this only works for our solar system, and I'm going to talk about this on our next slide, then what is the period of Earth? Well, the period Earth is 1. 1 squared is equal to 4 pi squared over GM sun times 1 AU cubed. That means this had better equal 1. When your period is in Earth years and your A is in AU, you get that all this stuff right here, this 4 pi over GM of the sun, becomes 1 and you can ignore it. In fact, I don't know that Kepler even knew what that was. Newton is the one who figured out what all that was. And we're going to talk a lot about how he figured that out. But for Kepler, he just noticed that in the solar system, T cubed or T squared is equal to A cubed, where this is in Earth years, and this is in what's called AU. Units don't match. 3 AU cubed is equal to Earth years squared. Kepler was a mathematician. He wasn't a physicist. A physicist, it hurts to look at that because the units are wrong, but that is Kepler's law. It only works in our solar system. If you were around some other sun and some other solar system, what you would have to do is T has to be in seconds, and it's the period how long it takes planet X to rotate around its weird star. And this would equal 4 pi squared, what we call the gravitational constant, mass of the star, times the semi-major axis cubed in meters. Okay, so doing this outside of our solar system is a little harder. Why would you want to do it? Well, let's talk about astronomy. I love astronomy. For most of human history, astronomy was simply observation. People were just looking at the light of stars and seeing what they could see. As the telescopes got better, we could actually see planets. We could see stars and calculate how they rotated around other galaxies. If you know how long it takes, which you can totally observe, you can observe a star or a planet. So if this is some star rotating around whatever the black hole is of its galaxy, you can figure out how far away it is from the center. And we have ways to figure out what that period is just by observation. We can figure out how long it takes a star to come back around, and therefore you can find how far away a star is from the center of the Milky Way. All you need to know is either the period or you need to know how far away it is. That's it. There's 2 there. So in practice, we now have RP plus RA is equal to 2A. RP, RA, remember close, far. We have equal area, equal time. And we have our final, which is T squared is A cubed, or not in our solar system. T squared is 4 pi squared over g mass of whatever, a cubed. So that's it. That's Kepler's equations. What I can ask of you with these is, I could give you RP and RA. Have you find A, have you find the eccentricity. If I give you, essentially I have to give you VA or VP. VA or VP. But remember that we also have 2 pi R over V. So if this is actually A, you could get some, I don't want to talk about that yet. I'm going to talk about it, but I don't want to talk about it as a math equation yet. And the reason why is you can actually find the average velocity. If you look on Wikipedia for like the Earth, it'll tell you what the average velocity of the Earth is around a star or around the sun. Average V is simply VA plus VP over 2. And once you have that, the period is actually 2 pi A over V average, just so you know. In fact, yeah, that's fine. Anyway, so what you do is you end up just starting with 2 or 3 of the variables and just putting them in these equations and getting the other variables. It's not too bad. We're going to do it. This slide is just converting, showing that in our solar system, this actually ends up just being 1 if T is in Earth years, and R is AU. T has to be in Earth years. So what you would get is you get pi squared times 10 to the 7th squared is 10 to the 14th. Second squared is equal to, AUs are 1.5 cubed times 10 to the 33rd meter cubed, for pi squared over g mass of the sun. Sun will be in kilograms. Therefore, if you have meter cubed over kilograms and you need to get seconds out, this g had better be kilograms over meters cubed. No, sorry, it's upside down. G is inverted. So G has to be 1 over kilograms meters. Yeah, 1 over kilograms, 1 over, nope, meters cubed. So meters cubed over kilograms times 1 over seconds squared. We're going to talk a lot about G, but G has some weird units to get it to convert to seconds. We'll talk about that when we get there. We'll also talk about what this actually is. But do you see something in here that you recognize? T squared is equal to 4 pi R cubed G over M. What is this? It's a volume. It's a volume of a sphere without the 3 on the bottom. So it's some kind of volume divided by mass. And we're going to talk about that later. I just want to plant the seed right now. So let's do a problem. We'll actually do Mars. Mars has, at aphelion and at perihelion, Mars is 1.67 AU away at RA, and it's 1.38 AU away at RP. We know how far it is from the sun. Obviously, that's not drawn to scale. That's almost circular. I mean, they're not too much different. And when it's at BA, Mars's translational velocity is 2.2 times 10 to the 4th meters per second. So we want to find A, E, T, A and AU, EY, and VP. Okay, so how do we do this? Well, we can start with AR plus RP is 2A, and we can get A. Or you could actually, well, or you could find the eccentricity, but let's do this first because we need A. So A is just half of the two added together. 1.67 plus 1.38 is 2.9, 3.05. 3.05 divided by 2 AU. These were both in AU. The answer's in AU. So this would be 1.525 AU. And hopefully, yeah, 1.53 is what I have. Okay, so we have A. Now how do we find E? Well, you could use RP is A minus EA, or you could use RA. The beautiful thing is, if you leave them in AU, it's easy. So let's convert this. This is actually A times 1 minus E, and this is A 1 plus E. It's actually probably easier to just go EA is A minus RP. So E is A minus RP divided by A, or 1 minus RP over A. That gives us E is 1 minus 1.38 divided by 1.525. Now, I have my calculator. 1.38 divided by 1.525. And then, no, 1 minus 1.38 divided by 1.525 is 0.095, 0.095. As expected, nearly circular. What is the period? Well, we have t squared is 4 pi squared over gm sun a cubed. But wait, if I want to be in Earth years, and if a is in AU, then I just need t squared is a cubed. So t is the square root of a cubed. T is 1.38 cubed. Take the square root. If I do that, I get the square root of 1.38 times 1.38 times 1.38. I get 1.62. 1.62 Earth years, okay? Or 1.62 times 365, 591 days for Mars to go around. And then finally, the last one is just VP RP is equal to VA RA. And if I want to find VP, I know VA is this. VP is VA RA over RP, which RA over RP, so 2.2 times 10 to the fourth times 1.67 divided by 1.38 is 2.66 times 10 to the fourth meters per second. You can leave RP and RA and AU, you can convert them, but you're gonna have to convert both denominator and the top and the bottom. So you might as well just leave them in AU. So as you can see, these are plug and chug questions if you know the equations. It's simply just start finding stuff. Start finding A, find E, find T, find BP. But there's a lot of info here. We realized that A is about, Mars is about 1.4 AU, 1.4 times the distance of Earth away from the sun. It's got a very low eccentricity of 0.095. That's nearly circular. It takes 1.6 Earth years to go around the sun for Mars. So about 1.5 years for it to go around. And its speed is pretty low. I mean, it sounds fast, 2.2 times 10 to the fourth, but that's actually pretty slow for a planet. But about typical. The Earth is somewhere close to that too. And it doesn't change that much. It's nearly circular. So the speed at perihelion and the speed of aphelion are essentially the same. And that's all there is to the Kepler problems. There's a lot to know, but it really just comes down to the following equations, which, like I said at the beginning of this lecture, write these down, put them somewhere. Make sure you know what these all are, but RP is A plus A minus EA. RP plus RA is 2A. RA is A plus EA. T squared is 4 pi squared over GM A cubed. If you're in our solar system, T squared is equal to A cubed, T in Earth year, A in AU. VARA is equal to VPRP. I think that's it, right? And then 1 AU is 1.5 times 10 to the 11th meters, and 1 Earth year is pi times 10 to the 7 seconds. Essentially, that's it. So you might need to be able to identify what A is, what RP is, and what RA is. Make sure you know that on an ellipse with one foci only. But the rest of it's plug and chug. And you're usually given one of the velocities and then 2 out of RP, RA, A, or E. The last thing to remember is if E is greater than 0.2-ish, not in our solar system. It wasn't formed in our solar system. And E has to be less than or equal to 1, greater than, I'm sorry, no equal signs. Has to be greater than 0 and less than 1. This is a parabola. This is a circle. So the last thing I'm going to say about this before we start talking about gravity, what if it was a circle? What if E was 0? What do all these mean? Well, you already know what these all mean, right? Because A is just R. All this stuff applies to a circle, just E is 0. And when E is 0, then you have R is A, RP is A, and RA is A, and therefore V is constant uniform circular motion. So you can do all this stuff with a circle, but why would you want to? It's, kind of ridiculous to do it with a circle. So that's the fun part of this lesson. There's a little bit more fun at the end when we do Einstein, but now it's going to come on some stuff that you might not have thought of about what we call universal gravity. At the very beginning of the semester, I'm pretty sure I asked you guys what gravity was, if you knew what gravity was. We're going to kind of see that Newton didn't know what gravity was. So going back to that first day story, Newton supposedly saw an apple fall. And what he asked was, why would it fall straight down? Why would anything fall straight down to the center of the earth? He actually came up with some cool math that we're going to talk about today that we didn't talk about before because we didn't want to talk about universal gravity before. But he realized that two objects are attracted to each other by something he called gravity, and he called it a force of gravity that attracted them. By simple reasoning, he reasoned that that force had to be equal to their masses, so mass 1 and mass 2. It had to depend on the square of the distance between them, and there was going to be some constant called g that maybe depended on other physics that we don't understand or we don't need to understand. Note that if F is ma and g is m1, m2 over r squared, I prefer you guys to write this as m1 g m2 over r squared, because you can immediately identify that a is g m2 over r squared. The acceleration on mass 1 due to mass 2 depends on mass 2 only. It only depends on the second mass. So the acceleration on you due to the Earth only depends on the Earth's mass. Me and you fall towards the center of the Earth at the same acceleration, even though we have different masses. A bowling ball and a feather have the same acceleration as long as they're at the same r. And that brings up a really important point. why we can't use 9.81 anymore, because we're going to assume that R can change, that you can get different distances away from the Earth. The moon is much further away from us than, or much further away from the sun, the center of the Earth, than we are. The moon feels a different gravity from the Earth than we do. And it has nothing to do with the mass of the moon. It has to do with the moon is very far away, where we're pretty close to the center of the Earth. Even being in the space station, gravity is significantly less than what we feel here on Earth, because they're very far away compared to us. Well, maybe not. Anyway, this G constant is called the constant of gravity, and it has a value of 6.67 times 10 to the 11th. Write that down somewhere, put it on a Post-it. You're going to use that over and over and over again. You need to memorize it. It just shows up all through everything. Remember, it showed up in the t squared was 4 pi squared over g m a cubed. It shows up everywhere. What are the units? If this is meters per second squared, and we have kilograms over meters squared, then this must be meters cubed over kilogram second squared. So it has some messed up units. No, the one that's boxed, it's GM. M here, Sammy, is whatever is causing gravity. For us, standing on the surface of the Earth, M is the Earth. For the Earth rotating around the sun, M is the sun. The force of gravity, remember, is your mass times your acceleration. So if we wanted the force on you due to the Earth, it would be that. But we just want the acceleration in this equation. And the acceleration only depends on the object that is causing gravity, not your own mass. What proof are you talking about, Sammy? This one right here? That one up there is the same. It's GM2 over R squared. It's not squared. It's, okay, so I want to tell you guys this. I want you to remember Newton's laws differently than you will almost always see it. Everyone says that the law of gravity says G m1 m2 over R squared. Okay, that's mass 1, mass 2. For two masses, 1 and 2, they're attracted each by a force. Everyone remembers it this way. But we're talking about motion in this class. And that force means m1 times the acceleration on m1. That is m1 times g m2 over r squared. I don't know where you're getting this squared from, Sammy. I think maybe you thought this was squared, but this m is not squared, it's m2. Yeah. But this is really important, you guys. You'll hear everyone say this. GM1, M2. Oh no, don't be sorry. It's fine, Sam. I'm not always clear. So ask, even there's no stupid questions. Everyone always cites Newton's laws as GM1 times M2 over R2. And I think that really obscures the fact that the acceleration on M1 is only due to M2. Don't forget that, where there are apart. And so let's do this for the Earth, okay? You're standing at the equator on Earth, right? And your mass is equal to, I don't know, 60 kilograms. The mass of the Earth is 5.94 times 10 to the 24th kilograms, okay? So what is the acceleration? Let's say that this is 6.4 times 10 to the 6th meters. It's 6,400 kilometers, right? So that's the distance from the Earth, or from the center of the Earth to you, is the radius of the Earth. Let's compute the acceleration. Does the acceleration depend on your mass? No, it only depends on the mass of the Earth. So the acceleration on you is 6.67 times 10 to the minus 11 times 5.94 times 10 to the 24th over 6.4 times 10 to the 6th squared. Now, forget about the numbers for a second. So A on U, 6.67 times 5.94 divided by 6.4 squared times 10 to the minus 11, 10 to the 24 over 10 to the 6 times 10 to the 6th is 10 to the 12th. This, if you look at it, ends up being just 10. Okay, 10 minus 11 times 10 to the 24th, you just subtract. So it's 10 to the 13th over 10 to the 12th. Whatever we get here, we're going to multiply by 10. What do you think we're going to get? 6.67 times 5.94 divided by 6.4 times 6.4, 967. So I get, writing it here, 0.9673 times 10 meters per second squared. If I multiply that by 10, I get 9.67. Why is that not 9.8? We'll talk about that in a minute. But what I want you to see out of all this is that the force of gravity between two objects is a third law pair. It does depend on both their masses. So 1 and 2. 1 is pulled this way by the force of gravity. 2 is pulled this way by the force of gravity. Equal force. However, A on 1 and A on 2, A on 1 is equal to gm2 over r2. A on 2 is equal to gm1 over r squared, where r is the distance from center to center. They have the same force, third law pair, but very different accelerations. Going back, what is the acceleration on the Earth due to you? It's g, your mass, over r squared. This was 6.67 times 10 to the minus 11. I think I said it was 60 over 6.4 times 10 to the 6th squared. This ends up being 6.67 over 6.4 squared times 60 times 10 to the minus 11 over 10 to the 12th. Okay, that is 10 to the minus 23. If I do the front part, which doesn't really matter, 6.67 times 60 divided by 6.4 times 6.4, I get 9.77 times 10 to the minus 23. That 9.77 is just a coincidence of the numbers I chose. But you're making the Earth accelerate by about 1 times 10 to the minus 22 meters per second squared, which is unmeasurable. The amount that you are accelerating the Earth is unmeasurable, but you are accelerating it. The amount that the Earth is accelerating you is pretty close to 9.8. So bear that in mind. The force of gravity will be the same between you and the Earth. You're causing just as big of a force on the Earth as the Earth is causing on you. The difference is that force ends up being divided by the mass of the Earth to give the acceleration of the Earth. The force ends up being divided by your mass to give the acceleration on you. So your mass is so insignificant that it makes a definite acceleration. The Earth and the Moon, we'll talk about in a little bit, but are pretty massive. And so you might think that would increase the acceleration on the moon due to the Earth, but it turns out it's actually less because r is so big. Anyway, that's all important. It's always a third law pair. There's something called supposition for multiple particles. And what that means, if you don't know what this term means, it's used a lot in math and physics. That means if we have 4 different masses, 1, 2, 3, and 4, okay? The principle of supposition says we can find the force of gravity on 1 is equal to the force between 1 and 4, plus the force between 1 and 2, plus the force between 1 and 3. You can just add all the forces as if they don't influence each other. So this is kind of a technical note, but you might think that, oh, I need to do this as some weird 3-body, 4-body problem. No, what's actually really nice about gravity is you can pretend like they're all completely isolated from each other and just sum them up. Now, that means that when you stand on the Earth and the moon is directly above you, right? And this is the Earth, you can find the force of gravity on you due to the Earth and the force of gravity on you due to the moon, and just add them together and get the total force of gravity on each other, on you. You don't need to worry about the fact that the moon and the Earth are influencing each other as well. That is supposition. It means you just treat everything as isolated, as if that's the only thing happening, and then you just add them all together. Those of you taking 4B, you're going to see supposition when you do what's called electrostatics, and you try to find the charge between 2 electrons or 2 protons or something, where you have multiple. For us, it's not that big of a deal. We just treat everything as if it's its own force pair, and then just sum them all together for what we want, okay? And in 2 dimensions, multiple particles. So there is one weird thing here that I want to say about this. So let's do it as you on the surface of the moon, or at the surface of the Earth. I don't remember how far away the moon is. Distance. So it's 3.84 times 10 to the 8th. Okay, so assuming this is right, 3.84 times 10 to the 8th meters. This distance we're going to still say is 6.4 times 10 to the 6 meters. So doing the force of gravity between you and the moon, and again, you have a mass of 60 kg. The Earth has a mass of 5.94 times 10 to the 24th kilograms, and the moon has a mass of forget this too. I don't want a fact sheet. I just want the mass. 7.3 times 10 to the 22nd. All right, so this brings up another point. Numbers get huge when we start doing all this stuff. You have to be good at your scientific notation. You can always leave the units off of G. They're hard to remember and they don't matter. So let's just do, this is the force of gravity on you due to the Earth, the force of gravity on you due to the moon. And we want to find the total force on you. So F of gravity is G, M of U plus M of whatever's causing it, R squared. So for both of these, we would have G times your mass, mass of the Earth, R to the Earth squared, plus G times M of U times mass of the moon over R to the moon squared. Now, here's the thing though. r to the moon from you would be r to the moon minus r of the Earth, right? If it mattered. And here it may, okay? So let's actually do this on the next page. We get 6.67 times 10 to the minus 11. I'm assuming you're 60. 6.4 times 10 to the 6th squared. Mass of the Earth, 5.94 times 10 to the 24th. Plus 6.67 times 10 to the minus 11. 60, what was it? 7.3 times 10 to the 22nd? Over, and now distance to the moon is 3.8 times 10 to the 8th, 0.84 times 10 to the 8th, minus 6.4 times 10 to the 6th. That is going to give me this is 384 times 10 to the 6th minus 6.4 times 10 to the 6th. So that would equal, what is that? 378, 370. You did that again to me, come on. 370, 7.6 times 10 to the 6th. So 377.6 times 10 to the 6th squared. Now, doing these, I'm going to do these as 6.67 divided by 6.4 squared times 60 times 5.94, 10 to the minus 11 times 10 to the 24th over 10 to the 12th. So this is 6.67 times 60 times 5.94 divided by 6.4 times 6.4 times 10. No, that should be, oh yeah, 6.67 times 60 times 5.94 divided by 6.4 times 6.4. This ends up being 580.4. This side, now why isn't this 9.8? Because it's the force. It's your mass times your acceleration. Is essentially 60 times 9.8, right? So this is the force of your mass times the acceleration due to the moon, due to the Earth. So 6.67 times 60 times 7.3 divided by 377.6 squared times 10 to the minus 11, 10 to the 22nd over 10 to the 12th. This is going to be 10 to the minus, or 10 to the 11th divided by 10 to the 12th. It's 10 to the minus 1. 6.67 times 60 times 7.3 divided by 377.6 times 377.6. Oh, are you kidding me? I did that syntax thing. 1.3 divided by 77.6 times 377.6. I get 0.0205 times 10 to the minus 1, or 0.0021, let's call it. Now, the force due to the moon and the force due to the sun, I'm sorry, force due to the Earth. Let's move these to a new sheet. So the force on you due to the Earth is about 580 newtons if you have a mass of 60 kilograms. You know that, and you're at the surface of the Earth. The force on you due to the moon is 0.0021 newtons. Think about that. Now, do you think you can feel, and that's with the Earth directly overhead, do you think you can feel the effect of the moon on you? I would ask, do you think that you can feel the effect? Anyone want to give an answer? And why? No one? That's okay. I'll tell you that yes, you indeed can, because when the sun is here, someone does. There's a really good way to prove this. If the sun is here and the earth is here and the moon is here, you do get tidal movement of the water. The water actually does get pulled a little bit to both sides. It does get a little bit of a bulge on both sides. And some of that, some very small amount of that, is due to the moon. A lot of it's due to the sun. Some of it's due to the fact that the earth is rotating, but you do get tides. And we see that tides happen twice a day, right? Why would they happen twice a day? Well, it's because of the way that the moon and sun are lined up. So when they're both lined up, you get much stronger tides, or maybe when they're not aligned, you get stronger tides. I always forget. It's the reason why it would seem to be completely like they would fight each other, but I feel like they actually resonate with each other when they're both lined up. You get bigger tides, even though it wouldn't seem like it when you draw a force diagram. But I may be wrong. It might be when the moon is 90 degrees from you or whatever. But because the earth rotates the way it does, you get stronger tides. The moon isn't a huge force. I mean, it's what, 10 to the 5th times smaller than the force of the earth on you, which is also why you don't get pulled away. But it is measurable. It is enough that if you had really sensitive equipment to gravity, you might have to worry about it, especially as you start going higher and higher up with like satellites and stuff. You might have to worry about the effect of the gravity of the moon. Okay, so we already said, we've already done this. If this is the radius of the earth, the force of gravity is your mass times the acceleration due to the earth. So the acceleration due to the earth is g, mass of the earth, over r squared. Now, g is 6.67. Mass of the earth is 5.97. I'll talk about that in a minute, why it's different than what I wrote. Squared times 10 to the minus 11 for g, 10 to the 24th kilograms for earth, 10 to the 6th times 10 to the 6th, 10 to the 12th. And this ends up being 10 here. And this ends up being 6.67 times 5.97 divided by 6.38 times 6.38 is 978 if you multiply by that 10. So why don't we use 9.78? We always use 9.81. Why don't we just use 9.78 instead? That is the mass on the surface of the earth. Well, it actually turns out that the earth is something called an oblate sphere. That means it's squashed. It's slightly fatter on the equator than it is at the poles. And in fact, when you go up to the poles, you're closer. So r at the poles is something like 6 point maybe 3. I forget exactly what it is, but it's something like 6.3 times 10 to the 6th. I don't want to do this again. But you find that gravity up here is about 9.83 meters per second squared. Gravity at the equator, when you're the furthest you can be from the center of the earth, is about 9.78. Is that right? This should be 9.84, sorry. 9.84 meters per second squared, meters per second squared. If you average those two, you get, oh my God, why does it do that? If you average these two numbers, the gravity at the pole and the gravity at the equator, you get 9.81. Now, cool thing about gravity. you can see from that that it depends on how far away you are. So if, and this was actually experiments that people did. So if you're on land, right, and then you go hiking up to the top of some mountain, gravity decreases. Why? Why does it decrease? Well, it decreases because your R to the center of the Earth, R to the center of the Earth plus R of the mountain, you've gotten further away. We're going to talk about pendulums in chapter 15, but you'll notice that even if you, I forget the guy's name, one of the really famous explorers did this, where he took a pendulum out and he hung it. And when he was on flat ground, it was straight down. And when he got close to a big mountain, it would kind of deflect a little bit. Because the force of gravity is no longer straight down, this mountain was actually attracting the pendulum as well as the Earth, which is kind of weird. Gravity's weird. What was Newton doing? Newton was trying to figure out how gravity worked on Earth, and he made a few assumptions that are ridiculous. He assumed that the Earth had a uniform density. The Earth does not have a uniform density. The core has different layers. The oceans and the continents are different. It's not a perfect sphere. It's an oblate spheroid. And the Earth is rotating. He assumed it wasn't rotating. When it's rotating, you get something called centrifugal forces. You already kind of know this from, why does it always do that to me? You already kind of know this from uniform circular motion, but an object that's spinning has to be pulled in, but you also have this tangential acceleration. And so your total acceleration ends up being something slightly different than just straight down. And therefore objects, if you don't account for the Coriolis force, you kind of get different numbers. People commonly know about the Coriolis force from the idea that toilets in Australia spin backwards. I don't remember if that's actually true because the water pressure has a lot to do with it in a toilet, but it's definitely true if you fired a rocket into the air. If you fired a rocket in the northern hemisphere, it would actually curve towards the North Pole due to the Coriolis force. It's why clouds spin. And if you fired it in the southern hemisphere, it would actually curve to the towards the South Pole. Those have to be accounted for if you're something like a forward observer in the Army who has to shoot artillery guns and target artillery guns. Anything that gets launched really high in the air actually gets a spin due to the fact that the Earth is rotating. And there's different reference frames and blah, 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 blah. It's a lot more than we need to talk about. But just know that Newton had to assume three things that are totally untrue. But he did. And he found a couple of really important things, okay? He found that if you are very far away from an object, it acts just like it's a point mass. So imagine you were really far away from the Earth, right? Essentially, all of these, oh, I should back up a second. So when you're actually, the problem that he had to solve is when you're standing on Earth, each of these little masses is also going to have a force of gravity. And supposition is still true, but you could have these little masses and you'd have to calculate them all. And you'd have an infinite number at a different radius from you. That's why Newton invented calculus. He realized he had to sum an infinite number of terms, and that's what an integral is. And he had to do it for gravity. So in a sense, gravity is what led Newton to invent calculus. Leibniz also invented derivative calculus, but Newton had to invent infinite sums. Newton did everything way harder than it should have been. He tried to do it as hard as possible, and he figured this out. But when you're really far away, those infinite sums all become just almost identical terms. When you're so far away that essentially for every one of these masses, so when you're so far away, the R is essentially the same. It acts just like they're all one point at a distance R with the total mass, right? I hope that makes sense to you guys. He figured that out, that when you're really far away, you can treat things as if they're just the center of mass. All of their mass is acting at the center of mass. Turns out you can treat them almost that way in general. Then the next thing he figured out, and this is kind of clever, is that when you start at the center of a point, so at a center of a shell, right? Every single one of these, if it's uniform, is going to cancel, right? So there's no force of gravity at the center. So let's say you move out a little bit of a radius, right? Still the same. But what you start doing as you move out of these shells that get bigger and bigger is you start to realize that all the exterior forces cancel, and only the ones inside within your radius matter. And you might think, well, how does that help? And we'll talk about how that helps in a second. But basically what he found was only the mass inside your radius counts between two bodies. Now, you can still have the moon above that would be pulling you, but so as you fall into a hole in the earth, basically, the deeper you go, the less mass is actually attracting you. And that's because the force of gravity ends up pairwise canceling. So think about if you were, even if you were here, yeah, all these would be strong, but you would have far more of them out here. And it turns out you can actually prove that mathematically, that all of the forces outside of your radius cancel. Everything inside acts like a point mass at the center for spherical objects. He figured that out, and that's really, really, really cool. That may be one of the most important things he figured out, although he figured out a ton of important things, is that inside an object, if you're at the center, there's no gravity. That was one of those things that that this problem came up, and this problem is mentioned in a lot of books. So there's this idea that you could drill a hole through the earth, right? And you could drop an object and it would shoot out the other side, right? And it should accelerate faster and faster and faster and faster, right? Well, no. If the force of gravity were simply Gmm over r squared, as r goes small, a should go to infinity. So why doesn't it? What do we have to do to fix this so that if you fell through the middle of the earth, as you went through the center, you wouldn't have an acceleration of infinity? Newton already proved that there's no acceleration at the center. There can't be, because all of the gravity forces pairwise cancel. Yet this, Newton's law, says that it would get infinite as you approach the center. Well, the solution is that we have to have a uniform density. So uniform density means that the density is mass over volume. Volume for a sphere is 4 pi r cubed. 4/3 r pi r cubed. And that also means dm over dv would be, but we don't need that so much. Now, when you're inside, okay, your mass is dependent on the volume, and the volume is 4/3 pi little r cubed. Now, that is inside mass, okay? The whole mass is big R. So when we do that, what we have is A is actually the mass of the Earth inside over little r squared, okay? Now, if we do this, since the density is mass over the volume of the whole Earth, this is m, and so then rho v inside is, which is your mass inside. Sorry if you're not following this. Let me go to this. So the mass inside is equal to the density of the Earth times the volume inside. That should make sense to you. And the volume inside is equal to 4/3 pi little r cubed. The volume of the Earth is 4/3 pi r of the Earth cubed. And rho is m over v of the Earth. So this becomes m v of the Earth v inside, which is m times 4/3 pi little r cubed over 4/3 pi radius of the Earth cubed. So let's write this as m inside is the mass of the Earth times little r cubed, big R cubed. Little r cubed is wherever you happen to be. If you're at the center of the Earth, it's 0. If you're at the surface, it's r Earth. Going back to here, so going back to here and plugging it into our equation of A is G mass inside the Earth over R squared, R inside, little r. And we just said that this was mass of the Earth times little r cubed over radius of the Earth cubed divided by r inside squared. So that means that A inside, A inside the Earth would be G m Earth times r, 2 of them cancel, but you're left with 1, divided by r of the Earth cubed. A at the surface, where r is equal to r of the Earth, would just be G m of the Earth over re squared, which is exactly what Newton showed. And anywhere else, it would just be Gm Earth over r squared, where r is greater than the Earth. Notice that that means when we get to the center of the Earth, little r is 0, and we get the acceleration is 0, as we should. This is a problem worth understanding. It's a kind of fun problem if you like doing the math. It only works for uniform density, unfortunately. So it doesn't work if you were trying to figure it out. So we arrive at, if little r, where you're at, is less than the radius of the Earth, then A is mass of the Earth over radius of the Earth cubed times little r, with the G, obviously. If you're at the surface, the boundaries have to match, okay? So that means that at the surface, little r is the radius of the Earth over radius of the Earth cubed. I think I skipped it by writing out the work. Yeah, I talked about all that here, Sammy. Yeah, at the boundary, r equals radius of the Earth, so you get Newton's normal law. And then whenever r is bigger than the radius of the Earth, you just get that. That's really important. This is important to know, but you'll never have a question on it, I don't think. So now that we found this, notice that if G is now big G m over r squared, this doesn't work anymore. So when we do this, we have to do, this is the one hard part in this whole chapter. we've got to do something totally different with our potential energy now. So you know how before we said, oh, in free fall, we can just write mgh if v initial is 0 and mv squared at the bottom here. We can't do that anymore. There's a subtle change that we need to make. Because the force of gravity, or the acceleration of gravity, is no longer a constant g. So potential energy. When you get potential energy is always the integral of the force times dx, right? Remember, it's the work. Work is F dot dx. We're calling it R here just because we're in a different world. So our force is gm m over r squared. Gm and m are constants over dr. That is equal to gm m dr over r squared. Now this, right, you go up one, well, this is r to the minus 2. So when we go up one, we get minus gmm over r. And if you want to put plus a constant, in physics, we almost never write that. But you can see this becomes the solution from r initial, I'm sorry, r final, r initial. And that means that, that the potential energy is equal to, looking at this, negative gmm over r final minus a minus plus gmm over r initial. And so you might be thinking, oh, that's just the negative work. No, not quite. We have a problem here. When we have this thing falling, h equals 0 wherever we want. Okay, we can put 0 wherever we want because really what we care about is we're saying that the change in kinetic energy is equal to the change in mgh, right? The change in the work, and the only thing we have to assume is that y is positive up if g is down. But we can't do that now. Now we have to do something clever to get our r to be 0. So we want our gravitational energy to be 0 at a certain point. So let me draw this. So imagine center of the Earth, and we're going to put you somewhere, and we want gmm to be 0 somewhere. Now, that becomes kind of difficult to understand, to be honest with you, where we put our 0. It doesn't work like h. The thing is that as we go this way, we're going to do work. We're going to add energy, okay? So if you remember that when we said here, what we were really saying is at this point, if it goes to here, it has this much potential energy. This is potential energy as well. And we want the potential energy to be 0 when it's really, really far away, okay? When r is equal to infinity, gmm over r is equal to 0. If I put in a huge number in here, then it's 0. So therefore, our potential energy is 0 when we are really far away, and it's the biggest it will be when r goes to 0. So it becomes gmm over r becomes infinity when it reaches when it reaches the center of the planet or whatever causing the gravity. As we move away, we do negative work. We do negative work as we move something against gravity. We already know that, right? So the change in kinetic energy, right, is negative as R increases, right? Or, better yet, to put this, should be equal to the change in potential energy, which means that we get here, normally we would write final versus minus initial, and we're still doing the minus sign. But it turns out that this ends up being negative work. So it's negative GMM over R final minus or plus GMM over R initial, which means that in this case, it's actually totally true. We now get MV final squared over 2 minus GMM over R final is equal to MV initial squared over 2 minus GMM over, R initial. So now, look at this. This is your kinetic energy final. This is your potential energy of gravity final. Before, we would have written like this, okay? Is equal to MV initial squared over 2 plus MGH initial. That doesn't work now because we have to choose that the potential energy is 0 when it's very far away. Gravity cannot do any work when you are very, very, very far away. When you're on the other side of the universe, you're not going to be pulled by the gravitational force of the sun. It's not going to do work to you. So when you're very far away, it has to be 0. And that ends up introducing a negative sign in the potential energy, which means it's not the same as before. Does this work? So let's write it slightly differently. Does MV final squared over 2 minus MV initial squared over 2 give us GMR initial minus, R final minus GMM over R initial. Now let's do 2 cases. An object moving from very far away to the center of the Earth. So R is, or to the surface of the Earth. R is initially infinity, and R final is just R of the Earth. What would happen to this delta KE? So GMM, I'm really going to write it as this, okay, is equal to the change in kinetic energy. Well, if R initial was infinity, this term becomes 0, and all this gravitational energy becomes a change in potential energy, and the object speeds up. So as you're falling towards the Earth, you're changing your kinetic energy. So the signs are right. What if we went the opposite way? So now, instead, this becomes R initial is Earth, and we get to R initial is equal to R Earth, and R final is equal to infinity, right? So now what happens is R final becomes 0, and we get a negative potential energy change, which slows us down. Launching something into space away from the gravity of the Earth, you lose your velocity. Gravity does negative work on it. So these signs are correct. This is important, super, super important. If you're used to writing the energy as mv squared over 2 plus mgh, remember it's now mv squared over 2 minus gmm over r. So now the energy is written as mv squared over 2 minus gmm over r, where r is taken from the center of whatever mass is causing gravity. Something we should note here, remember that A is equal to G big M over, so let's cancel these for a second. A is equal to G M over R squared. That came from little ma is G big M little m over R squared. So therefore G M is a R squared. This was all to prove that that negative sign, Sammy, is correct. Yeah. That this negative sign right here is correct because we used to write it mv squared over 2 plus mgh. It's now mv squared over 2 minus gmm over r. So if G big M is AR squared, and I totally should have got rid of the other one, little m's, then I can write this as V squared over 2 minus AR squared over R is equal to the energy. Okay, so V squared over 2 minus AR squared over R means V squared over 2 minus AR is equal to the energy. I'm going to put the little m back because I realize that's not actually the energy without that little m. Okay. So what did I want to show here? Oh, actually, I went the wrong way. I'm so sorry, you guys. Let me do this. mv squared over 2. Remember that v squared over r is equal to a, which is equal to big G over m over r squared. Okay, so let's multiply by r over r. And what we get is m a r over 2. But if you plug that in, you get g m little m over 2r squared times r, which is gmm over 2r. That means mv squared, when we're talking about gravitation, is equal to gmm over 2r. Keep that in mind. We said that the energy at any time is mv squared over 2 minus gmm over r. Okay, big R. Well, if the energy is gmm over 2r minus gmm over r, this is mv squared, this is gravity. That means the total energy is gmm over 2r with a negative sign. That's weird, you guys. Okay. A satellite going around the Earth has an energy of g m of the Earth, m of the satellite divided by 2 times whatever the radius that it's rotating at, with a negative sign. It has negative energy. That's because to get away from the center of Earth, it required you to put energy in. To get away, you have to put energy in. So it's how much energy was required to get the object up there. What you need to remember from this is these 2 parts of this equation, this part and this part, that for something that's rotating, it has that energy. And then, and that's its total energy. And then you can do something like the energy total is minus gmm over 2r. Energy 1 and energy 2 will be at r1 and r2. So you could do surface of the Earth and far away, right? And infinity and whatever, r Earth, whatever. What you do is you write down minus, mv squared over 2 for 1 minus gmm, and these are, I should really do little m's. The m's get a little wonky. Big M's are Earth over r, 1 m v2 squared over 2 minus g big M little m over r2. And you know that they're both equal to this, okay? So this stuff is messy and hard and weird. It takes a while to get comfortable with it. And the fact that it's negative, really weird. So this is just saying that if we want GM over R to be 0, that only occurs when R is infinite. So we have to start as if infinitely far away, our potential energy of gravity is 0. This is all about moving against. I've already done all that, kinetic energy. Just go back through it. So it brings up a really good question, though, or point, or interesting fact. So if we say that an object on the surface all those equations that we wrote down were just to prove Sammy. Yeah. I told you guys at the beginning of this, there's very few equations you need to remember, but proving this might help you actually understand this better though. So imagine at the surface of the Earth, you have energy 1, and Sammy, I'm not going to tell you what you need to know. Just go through the book and learn what you need to know. I am telling you that you only need to know the equations. There's 5 equations for Kepler's law. For gravity, G mm over r squared. You better know that the acceleration of gravity is G times whatever mass is causing it over r squared. And the potential energy of gravity is G mm over r. This you need to know that this is what you need to know. R is at infinity, and if you write the energy, it is mv squared over 2 minus gmm over r. This is little m. So you know what I'm going to do is I'm going to m and v. Black m is the mass of the Earth. Little m is whatever yours is. So let's look at this. Imagine you're at the surface of the Earth. So your radius here is the radius of the Earth, okay? And you want to go to a radius very far away, where your radius goes to infinity. All right, so the energy here is mv. Let's call this energy 1 and energy 2. mv1 over 2 squared minus gm mass of the Earth over r1. And the energy here is mv2 squared over 2 minus gm m of the Earth r2. But r2 is infinity. And we're going to assume that it's going to be launched so that it reaches infinity at 0 speed. That means v2 will be 0 and r2 will be infinity, and these will become 0. So energy 2 is equal to energy 1. And that means 0 is equal to m v1 squared over 2 minus g m of the Earth over r1, which is actually r of the Earth. Since this is a negative sign, I'll just move it over and set them equal to each other. Since they both have this mass cancels. And since this is my v, I'm going to multiply by 2 and take the square root. So I'm going to multiply by 2 and take the square root. What I get here is that v, the launch speed to reach infinity for an object, does not depend on the mass of the object. It merely depends on the mass of the planet itself and the radius that you're launched from. Why is this important? Why would you need to know what speed it would take to reach infinity? The reason is This is something called an escape speed. It's more commonly written, I kind of have it written weird there. It's more commonly written like this. V escape speed is square root 2g mass of the Earth or mass of whatever you have. So this could be the mass of Jupiter over the radius of Jupiter. This is called the escape speed. It's important because that is the minimum speed you would need to escape. On a planet like Mercury, that's very small, it has a very small mass and a very small radius. Remember, G is 10 to the minus 11. It's going to be very small. The escape speed from Mercury is very tiny. The escape speed from Earth is moderate. What would try to escape Earth before astronauts? Gases like oxygen. So whether or not a planet can keep its atmosphere depends on the escape speed. Let's look at the escape speed of Earth. For Earth, the mass of the Earth is 5.94 or 7 times 10 to the 24th kilograms. The radius of the Earth is 6.4 times 10 to the 6th meters. G is 6.67 times 10 to the minus 11, bunch of units. So V escape from Earth would be 2 times 6.67 times 5.94 or 97, depending on where you look on the internet, times 10 to the negative 11, 10 to the 24 over 10 to the 6. Now, what's in the parentheses is 2 times 6.67 times 5.94 divided by 6.4. 10 to the minus 11 times 10 to the 24th is 10 to the minus 13 divided by 10 to the 7th is 10 to the, or 10 to the 6th is 10 to the 7th. So this is 12.38 times 10 to the 7th. Put that in my calculator and take the square root, and I get 11,100. 11,100-ish meters per second. Now, 1,100 or 11,100 meters per second seems really fast, right? You might think. If you do it for all of the planets at their equator, their equatorial radius, with the mass and with the radiuses, Earth is about 11,000. Mars, which is significantly smaller than Earth, is only got an escape speed of 5,000. The moon only has an escape speed of 23,000 or 2,370. The moon has no atmosphere because the escape speed is so low. Jupiter is made of hydrogen. It has an escape speed of 59,000, almost 60,000 meters per second. That means oxygen molecule would have to be doing 60,000 meters per second at the surface of Jupiter to get away, and gravity can't pull it back. So the root mean square speed of hydrogen is 200 or 2,400 meters per second. Oxygen is only 461. We said the escape speed of Earth was 1,100 or 11,100 meters per second. So how can hydrogen possibly be going fast enough to escape from the Earth, or oxygen? You guys that are in chemistry already know this. Root mean square, these are average speeds. So the velocities look like this, right? Most of them are doing, this is the number of molecules. Most of them are doing 2,400, but there's a few that are probably reaching 11,100 meters per second. There's a few oxygens. The oxygens are on average doing 461, but a few of them are going fast enough to escape. If we look back here, you can see that on the moon, everything escapes because it's not very hard for hydrogen or oxygen to go fast enough to get off the moon and leave the moon forever. Remember, V is the escape speed, which means it will leave forever. It will never come back, right? So you can literally use that energy equation, the energy equation of mv squared over 2 minus g big M over r. You can use that to find the escape speed from the surface of a planet, and that will tell you whether or not it still has an atmosphere. The Earth's atmosphere is almost gone if you really look. It's very thin. Venus has a pretty respectable atmosphere, but that's because it got a runaway greenhouse effect that's doing some weird things. Jupiter has a huge, Jupiter is mostly, it's a little rock in the middle of a huge gas cloud. It's almost all atmosphere because it's so massive that hydrogen can't even get away. The sun too, hydrogen can barely get off the sun. So it's neat to use something so simple as potential energy due to gravity describes exactly why things have an atmosphere. All right, so all of this, we only have one last thing, and then I want to go over the homework that I assigned. But this is what is gravity. Newton had a problem. For those of you that are here and paying attention, if I do this with my fingers and something falls over in your house, right when I do that, your book falls over. You wouldn't think that there's any way that I caused your book to fall over just because I snapped my fingers here. The reason why is force at a distance. Other than magic, there's no force at a distance. You can't affect something if something isn't traveling from you to that object, right? Newton believed that. He said that force at a distance is impossible. Something has to travel between two objects for them to affect each other. But gravity means that two things are affecting each other over a great distance. They're both affecting each other with the same force, but what's going between them? So, I mean, this is kind of a mean example, but if I punch you, my hand is actually making contact and changing your kinetic energy. In fact, electricity is run off of photons. Photons are transferred between electrons and atoms and stuff, and they are the force carriers of electromagnetism. So what is the force carrier of gravity? It seems weird that Newton couldn't figure this out. Well, gravity is not actually necessarily best described as a force. It's better described as a space and time field. Now, if you've ever heard of this, great. If you haven't, look it up. There's a book called Flatland. Flatland is about two-dimensional creatures living in a three-dimensional world. It's a fantasy book by a mathematician. But if you only lived in two dimensions and you saw a circle, or I'm sorry, you saw a sphere intersect with you, it would just look like a circle, right? So if you were in two dimensions, you would see a circle and think that's a sphere. It sounds weird. If you think about it, it kind of makes sense. Essentially, what gravity is that we actually live in a four-dimensional world called space-time. And what happens is mass causes a disturbance in the field of space-time around itself. The best analogy is the bowling ball on a bed analogy. If you place a bowling ball in the center of your bed, it'll push down the area around it. And if you then roll a ball, as you can see in this picture, if we roll a ball through here, if it gets too close to the well where the bowling ball is, it'll actually force it to curve. If it's not going fast enough, it'll actually just sit and spin around and around the bowling ball. Eventually it falls in, but that's because of friction. So what essentially is happening is this is just like the sun. The Earth is going around the lip of a well around the sun, and it's trapped there forever. But the Earth is traveling in a straight line. It's just traveling in a curved space-time. So the Earth's orbit isn't curved. Reality is curved around the Earth's straight orbit, which sounds so weird, I know, but that is what it is gravity is more of a field. There's tensor equations that describe it. Einstein actually realized this. Einstein realized there had to be something called space and time, and that at a certain point, space and time are so connected that they are inseparable. We know it's true because if you see a solar eclipse, what's really weird is, and this is trying to show it, but let's say that there is a galaxy blocked by the sun. So the sun's blocking it. During a solar eclipse, when the moon passes directly, by a weird chance, the moon, the exact same size, it completely can block out the sun if they cross paths. But when the moon completely blocks the sun out, you can actually see stuff that's, we know is behind the sun. It's something called gravitational lensing, and it's because, as you see in this picture, as an object's light comes in, it gets bent around the sun. And so an object that's behind the sun, we can actually see them on an eclipse. The sun's just big enough that you have to be able to block the sun out and get just, it's pretty close. The bending isn't as big as you see here, but it's completely true. Space-time gets bent by masses. They've done a lot of work with bosons and other particles trying to figure out exactly what mass is, how mass works. They've made some breakthroughs in the last 5 years. But it's a little weird to think about that essentially in the Earth's rest frame, the Earth is traveling in a straight line and reality around us is curved. And that's why we rotate around the sun, because space itself is a bowl, not a flat plane. If you guys are interested in a lot of this gravity stuff, I suggest you take some astronomy. Astronomy is all about gravity and how huge masses cause gravitational waves and things like that. It's really cool. It's really, really nice. And this chapter with the true gravitational formulation and the potential energy of Newtonian gravity really is a nice foundation to get into an astronomy class and understand. You also need to understand light waves, but for the most part, if you can get this stuff, astronomy will be a lot of fun and not a lot of math, which is cool. Anyway, so that's all well and good on chapter 13. As I said at the beginning, Newton saw an apple fall and he wondered why. He came up with forces and accelerations. He proved that there were things like momentum and even angular momentum using Kepler's data, which is even more fitting if Kepler killed Brahe, that Newton came along and figured out what was really going on instead of just using math, meaning instead of just modeling the data. Newton came up with theoretical equations to explain it. But Newton still didn't understand force at a distance, and Einstein came along and said, well, what if it's not being force at a distance? What if it's just that it's curving reality itself? And pretty weird stuff, pretty hard stuff to wrap your head around if you can't see it. I urge you to read books like Stephen Hawking's, various books. He has many books on this stuff, relativity. Read books on relativity, read Flatland, and enjoy it now that you have kind of a basic knowledge of it. And take some astronomy if you have no other classes to take, and you can find an astronomy class somewhere. Okay, so let me go to the homework really fast that I signed. chapter 13. So I just assigned this yesterday. It's due a week from Sunday. I just want to, I'm not going to solve any of this. I just want to give you some hints about maybe strategies on these. There are 10 of them. Don't freak out though. A lot of them are super easy. So Sun and Earth each exert a gravitational force on the moon. What is the ratio of Sun, Earth? So just put the GMM over R squared, but make sure you have the right radius for Sun and radius for Earth and the right masses. How far from Earth would you have to put a probe so that the Sun and the Earth, so that there's no gravity, it's not being pulled either way? So figure out, just set the two equal to 0, and you'll get, make sure one of them is negative, and you'll get a right answer. So those two shouldn't take very long at all. Frank Lloyd Wright was an architect. He wanted to build a building that went up. So what we want to know is, if you went up in an elevator and you weighed 821 newtons, so remember your weight is mg, but now your weight is gmm over r squared. Remember that the radius is the distance to the center of the Earth, not just the top of the building, okay? You need to find the radius from the center of the Earth and the building. It'll make more sense when you try and do it. Here's a planet, and you're told that a probe, a 10-kilogram probe, you're given the radius of the planet, its mass, the probe of the mass of the probe. You're told that if it's launched with an initial kinetic energy from the surface of the planet, you're given what its kinetic energy will be, and then it wants to know, so you know the kinetic energy, mv squared. You can find gmm over r from the surface radius. Then when it's kinetic energy, what is it kinetic energy when it's this r? So you just have to find mv squared when this is r final. It's not too hard. If it gets a maximum distance of 8 times 10 to the 6th away, what is the initial kinetic energy at the surface? Don't forget that it's going to have gmm over r at the surface with a negative sign, okay? It's not too hard. Mean distance, so A is your mean distance, is 2.64 times that of Earth. You can put 2.64 AU. The distance from Earth to the Sun is AU. From Kepler's law of periods, T squared equals A cubed. Calculate the number of years it takes for the asteroid to make one revolution. Now, T in Earth years, T squared is equal to A in AU, A cubed. So T squared equals A cubed. This is 2.64 AU. Yours may be different. 6, we're told that a comet was seen in 596 AD in China, and then again in 1921. That is a difference of 13.25 years. That is the period. The comet has a period of 1,325 Earth years. And you're given the eccentricity. So from that period and that eccentricity, find the semi-major axis, A, as in A and R Kepler laws, and find the distance, the greatest distance from the Sun. The greatest distance is this aphelion distance, okay? So find RA. For 7, we're given the eccentricity and the semi-major axis. Again, this is your A in your Kepler's laws and your E. The Sun's center is one focus. How far to the other focus? So now this is something we didn't talk about, but the center to one focus is EA. So the center to the other focus should be EA, and therefore the distance between them should be 2EA. What is the radius of this distance to the solar distance? That's blah. Satellite circles a planet every 6.21 hours. Turn that hours into seconds. And you get the period. The magnitude of the gravitational force is 116 newtons. You probably got something different. So from that, you should be able to find the radius, the kinetic energy, and the mass of the planet. Remember, the total energy is negative GMM over 2R. Okay, so that should help. Satellite in elliptic orbit about this planet at aphelion radius. The angular speed is that. Remember Newton's second law, or Kepler's second law in Newton's form. VARA is VPRP. It's not too bad. And then finally, projectile fired with an initial speed, how far will it go? In this one, assume that when it gets to its final R, that its velocity is 0. So mv squared over 2 will be 0 wherever it ends up. So you'll have, it's on the surface of the Earth, okay? So it'll have mv squared initial, mv initial squared over 2 minus gmm over r of the Earth is equal to mv final squared over 2, but that's 0, minus gmm over r final. And they want you to get r final. So those are the 10. Seems like a lot, but it's actually not too bad. Pay attention to the Kepler stuff, and we'll do a Kepler problem for the quiz on Tuesday. So it'll be something where you're given like the perihelion radius and the aphelion distance, and I'll want you to find the eccentricity and the semi-major axis. Any questions on anything before we get out of here? One thing I will say, I'm going to grade your tests on Sunday. I've got to do some stuff Friday and Saturday. So I'll be grading Sunday and Monday, and hopefully have them all done to you by Tuesday. And yeah, other than that, I'll see you all later unless you need anything from me.
Professor?
Yes.
I have a quick question about the lab.
Mm-hmm.
Okay, can I share my screen?
Yes.
Okay, thank you. So as we talked before the class, this is delta F. I calculated based on based on this formula.
Right.
Then I filled out all the tables. Oh, I just need the slope uncertainty. This comes from the Excel, right?
Yeah, it comes from the LinEst.
Could you see my Excel right now?
No, you're only sharing your, yes. Go to, you would need to share your Excel.
Okay. Let me share my.
So just stop share that and then share your Excel.
Yeah. So this is uncertainty.
No, that is for B. So your slope is 0.5775, the top, yeah. Right below that is the slope uncertainty.
But this is uncertainty.
Yeah. So the negative 0.047, if you look at your trend line, that's your B, or your y-intercept when x is 0. And then the two numbers below them are the uncertainties associated with each one. So on the left, it's slope uncertainty, r squared value.
So
I don't know what the bottom two are. I know the 2 is
actually I search on the internet. That's why I say this. Let me show you that one. Sorry.
Yeah, sure.
So stop sharing, and then let me. I found this. Yes, this one. Okay. Share. So, could you see this one?
So.
Well, here, let me. This one, that would be better. Oh, it's very small. I think you can't see that.
That's okay.
Oh, here. So it says uncertainty. This one below this.
Yeah,
one.
that's the y-intercept though. So see here on the left, it's slope uncertainty.
It says uncertainty. Okay, uncertainty.
Yeah, they had a typo. But yeah, so see that. So that's cool. It gives you the standard error as well. it gives you the residual, it gives you the regression, it gives you the F stat. If you know stats, all that stuff's cool. But
Yeah.
all you need to know for us is that that will give you the slope and the trend line because it gives you the y-intercept.
Yes.
Only works for linear trend lines though, y equals mx plus b. I don't know what you do for like a quadratic, but
Oh. Uh-huh.
yeah, there's probably a way to get the uncertainties on the quadratic functions too. Um,
Uh-huh.
I don't know why Excel doesn't just give that to you. It seems like kind of
Yeah.
important and no reason to keep it, but
Okay. So when I fill this one too, so I have to change this number with the
and just do
one.
do the 3-digit sig figs. So just
Okay.
do the first like 0.008, whatever it was, the first
Okay.
3 figs.
Three
You don't need
digits.
to do the
Yeah.
rest of them.
Okay. So we have this one. We have this one. So I filled out. Oh, here I need just this one,
Yes,
and this one comes
that
from this.
big
this
ugly thing. Yeah,
Okay. So slope uncertainty, I know slope uncertainty. I know, oh, and this one, I know this one, this is exactly this one.
right. Yeah, it's just
But
the
times by F,
triangle F times F again.
times by F,
Yeah,
right? And the others
are
are,
0.05 millimeters, but since your R's are in centimeters, it's
yes.
0.05 centimeters. I mean, um, make sure you leave your length or your R, your L and R's in centimeters. The delta
Oh,
R and the delta F would be 0.05 centimeters. I'm sorry, the delta L and the delta R would be 0.05 centimeters, as long as all your R's are in centimeters, okay?
oh. So for example, here, R1, which is R1 is L,
Yeah,
and
yeah,
R2 is 2/3 L.
right, yeah,
So when I want to calculate this one, delta R1 over R1 is 0.05 over 30 centimeters.
yes, sir. Got it.
0.05, or delta L is 30 centimeters over this one.
Yes. Oh,
Okay.
no, but your delta L is 0.05.
Delta L, yeah, yes, 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 yes.
Sounds like you got it. I know that equation is awful. Can we go down and look at your table really fast, though? Your results? No, the other way.
This
Uh,
one?
yeah, so your penny mass is pretty good, and your ruler masses were almost dead on. Awesome. Cool.
Thank you.
Yeah, some
Thank
of
you.
us, me and Sammy found out yesterday. I think that if the ruler's too heavy, the results are really horrible. So I just want your results look good. So
Thank you.
you're welcome.
So, okay. Thank you so much. Have a good day.
You too, sir.
Oh, so you post the solutions for the exam on this Sunday, or
Yeah,
maybe Monday.
post on Sunday. Before I grade it, I usually rewrite them and then I grade it from that. And I usually check a couple of the exams just to make sure I don't make a mistake on the grading. Because sometimes you guys
Okay.
figure it out better than I do, and I realize I have a mistake. Yeah, it happens. Writing questions
What do you?
myself is horrible, but since you guys all have internet access, I can't, use questions that are online. Anyway, I'll see
Okay.
you guys soon.
But you don't do. But you don't post the solution for question 3 because you omit that one.
Yeah, the if you wanted to try and do it yourself, just make the force like 7 newtons, is what I intended. It looks to me like what I did was I forgot time when I wrote F, or the torque times time equals I omega. It looks in my solution like I forgot to multiply by 0.03, and that messed everything up. So, or zero point 0.3. Um, but if you wanted to try it, use a force of like 7 newtons, and it'll end up being what I wanted. Anyway,
Okay.
talk to you guys soon.
Thank you much.
I guess.
Thank you. Bye bye.